Hello, let's get started on Chapter 4, Systems of Linear Equations. Remember to print out the corresponding lesson handout so you can follow along and work through the problems as you view the videos. Chapter 4, Section 1 is on systems of linear equations in two variables. Our objectives are to decide whether an ordered pair is a solution of a linear system, as well as solving linear systems by graphing, substitution, and elimination. Our final objective is to solve special systems. Here's an example of a word problem that can be solved using a system of equations. Suppose we wish to cut a 10-foot length of conduit into two pieces such that one piece is 4 feet longer than the other. We are looking for two numbers whose sum is 10 and whose difference is 4. A conduit is simply a metal tube or pipe, and suppose we have a 10-foot length here and we want to cut it so that one length is 4 feet longer than the other. We can begin by assigning variables to the lengths of each of those corresponding parts. And the fact that the conduit is 10 foot in total, we see that x plus y, the length x plus the length y, would equal 10. And the x is 4 feet longer than the y, so we say x minus y is equal to 4. We call such an arrangement a system of two equations in two variables. Now, one way to solve a system of equations is to figure out the right x and y, in this case by a guess and check method. We can guess, for example, say x is 8 feet. Then if the whole length of the conduit is 10 feet, then y would have to equal 2 feet. But that doesn't satisfy the second equation. If you subtract x minus y, in this case the difference is 6 feet in difference. So what we're going to do, let's try a different value. Let's choose a different x value. For example, let's say this x is 7 feet and y would end up being 3 feet. So the total length is 10 feet. And if you also notice that the 7-foot length is 4 feet longer than the 3-foot length. So the solution to the system of equations can be written as an ordered pair 7, 3, where x is equal to 7 and y is equal to 3, and both of those correspond to length measurements in feet. Now the original two equations, x plus y equals 10, is a linear equation, and x minus y equals 4 is also a linear equation. You can practice graphing those, and you'll see that our first equation, x plus y equals 10, is represented by this blue line. The second equation, x minus y is equal to 4, is represented by this red line. And we will find that the point where those two lines intersect is the point 7, 3. This is considered to be the solution to the system of equation, is that single point xy that lies on both equations, both lines. So we want to find the intersection. A way to check to see if our solution is correct is by replacing the x and the y in both equations and making sure that both equations are true. So here again we're letting x equals 7 and y equals 3. We see that 7 plus 3 does equal 10. That satisfies the first equation. The first equation is true. We're plugging in 7 for x and 3 for y into the second equation, and we also see that 7 minus 3 is equal to 4, so that second equation is true. So we say that the point 7, 3 is a solution to the system of equations because it satisfies both equations, making both equations true. In these examples, we're going to decide whether an ordered pair is a solution. Now, one way to do that is by graphing and finding the point of intersection. However, in these examples, we are given the points, and we want to determine if this point is a solution to the system of equations. In other words, when x equals -1, and y equals 3. And if we were to plug those into both of the original equations, we would want them both to be true equations. So that's what we'll do in this step here. I'm substituting. Instead of x, I'm putting -1 in the first equation, plus, instead of y, I'm putting in 3, and I want to make sure that that equals 1. And I'm looking at my first equation to determine if -1, 3 is a point that lies on that first line. We can simplify this equation to get -2 plus 3, that does equal 1, so it is true in the first equation. We also need to make sure that the same x and y is true for the second equation. So I'm going to replace the x with -1 and replace the y with 3 in the second equation. In this case, it's equal to 9. So -3x plus 2y equals 9, replacing x with -1 and y with 3, and simplifying this equation, we get -3 times -1 is +3, and 2 times 3 is 6. 3 plus 6 equals 9. That's true. So we can say that -1, 3 is a solution to that system of equations. Now let's do the second example on the right side here. We are looking to determine if the given point, 3, -1, is a solution to the system of equations. Making sure that we plug in x and y into both of those equations, both equations will be true. So our first equation is 2 times x plus y. I like to put, whenever I substitute in, I do like to put those values in parentheses. So I'm replacing x with 3 and y with -1. Simplifying this equation, I get 2 times 3 is 6. 6 plus -1, that does not equal 1. So we say that is false. So 3, -1 is not even a point on that first line. So we can say that 3, -1 is not a solution to the system of equations. In order for it to be a solution, this point must be on both of those lines. In other words, it must be true for both equations. Since the first one is not true, we don't even need to bother checking the second one. Now, systems of linear equations can be represented as graphs on a piece of graph paper, 2 lines, and there are several scenarios that could happen when you're graphing 2 lines on the same piece of graph paper. The first case is that the 2 graphs intersect at a single point. The coordinates of this point give the only solution of the system. Since the system has a solution, we say that it is consistent. The equations are not equivalent, so they are independent. So again, here, to summarize, one case is that the 2 lines will intersect at exactly one point. That point where they intersect is called the solution. The solution is consistent, and it's considered independent because it has a single solution. Another scenario is that the graphs are parallel lines. Our goal in solving a system of linear equations is to find out where those 2 lines intersect. But if the lines are parallel, they're never going to intersect. So there is no solution common to both equations. The solution set is 0 with a line in it. This notation is considered to be the empty set. And the system is inconsistent. Since the equations are not equivalent, they are independent. So again, if the graphs are parallel lines, we say that this has no solution. And the way we can write no solution is by using 0 with a line through it. Another scenario is that the 2 equations, when you graph them, end up being the same line. Since any solution of one equation of the system is a solution of the other, the solution set is an infinite set of ordered pairs representing the points on the line. This type of system is consistent because there is a solution. The equations are equivalent, so they are dependent. So essentially every single point that is on the first line is also a point that's on the second line. So there are an infinite number of correct solutions here, and we don't want to leave any of them out, so we say that there's an infinite number of solutions. Every single point that's on the first line is also a point on the second line. So the way we solve a linear system of equations by the substitution method is by following this 5-step process. We solve one of the equations for either variable. If one of the variable terms has a coefficient of 1 or -1, choose it, since the substitution method is usually easier that way. Step 2 is to substitute for that variable in the other equation. The result should be an equation with just one variable. Step number 3 is to solve the equation from step 2. Step number 4, find the other value. Substitute the result from step 3 into the equation from step 1 to find the value of the other variable. And our final step is to check the solution in both of the original equations, then write the solution set. We'll do example number 4, solving this system of equations using the substitution method. So going back to the previous slide, the first step is to solve one equations for either variable. You could either choose the first equation or the second equation. I'm going to choose the first equation. The reason why is because this y has a coefficient of 1. It's going to be a little bit easier to solve that for y. So I'm going to write the first equation, 2x plus y equals 2, and solving this for y by subtracting 2x from both sides of the equation. And the resulting equation is y equals, I can write this as either 2 minus 2x or negative 2x plus 2. So that's our step 1, is to solve one of the equations for either variable. Step number 2 is to substitute for that variable in the other equation. Since I used the first equation, I'm now going to use the second equation, and the y that I got in the first equation, I'm going to substitute in to the y in the second equation. That's going to look like this. 6, and I'm going to replace the, well, I don't need to replace the x. 6x minus 4, I'm replacing the 4, the y, with negative 2x plus 2 equals negative 1. So I wrote the second equation, but instead of this y, I replaced it with what y is equal to from the first equation. Now we're going to solve this equation for from this step. That's our step number 2. So step number 3 is to solve this equation. We have 6x, and I'm going to distribute that negative 4, and I get plus 8x minus 8 is equal to negative 1. I'm going to combine like terms to get 14x minus 8 is equal to negative 1, and then I'll add 8 to both sides of this equation to get 14x is equal to 7. By dividing both sides of this equation by 14, I get x equals 7 over 14, which can be simplified to 1/2. Now, to find the other value in step 4, we're going to plug this answer into that first step, into the equation from step number 1. So again, that from step number 1, we found y was equal to negative 2x plus 2. I'm going to replace the x from the last step into the x from this equation, and I get y equals negative 2 times 1/2 plus 2. When you simplify this equation, you get y equals negative 2 times 1/2, which is 1, negative 1, plus 2, and we get y is equal to a positive 1. So our solution to this system of equations can be written as the ordered pair 1/2, comma, 1. Now you do want to check to make sure that this is a solution to both of the original equations. All right, for the check step, I'm going to make sure the solution 1/2, 1 works, makes the first equation and the second equation true. I'm going to replace the x in the first equation with 1/2 plus the y of 1. Make sure that that equals 2. When you simplify, 2 times 1/2 is 1, plus 1, that equals 2, so that is true in the first equation. We also want to check the second equation, which is 6x. I'm replacing the x with 1/2 minus 4y, replacing the y with 1. That has to equal -1. By simplifying, 6 times 1/2 is 3. 3 minus 4 does equal -1, so this is also true in the second equation. So that verifies that our solution to the system of equations is the single point 1/2, comma, 1. Another method for solving systems of linear equations is by using the elimination method. This is a 6-step process. Step number 1 is to write both equations in standard form, where the equations look like ax plus by equals c. Step number 2 is make sure the coefficients of one pair of variable terms are opposites. And you can multiply one or both equations by appropriate numbers so that the sum of the coefficients of either the x or y terms is 0. Third step is to add the new equations to eliminate a variable, and the sum should be an equation with just one variable. Step number 4 is solve this equation from step 3 for the remaining variable. Step 5 is to find the other value. Substitute the result from step 4 into either of the original equations and solve for the other variable. Step number 6 is check the ordered pair solution in both of the original equations, then write the solution set. We'll go over an example now. So in this example, we're going to solve the system of equations by elimination. The first step in the elimination method is to write both equations in standard form. This is already done for us. Notice the ax plus by equals c. The x and y terms are on the left, and the constant term is on the right. We are going to need to make the coefficients of one pair of variable terms opposites. Now you can either get opposite x terms or opposite y terms. For this example, we'll go ahead and get opposite x terms. To find the correct x terms, we want to take a look at what we have to start off with. We have 2x and 3x. We want the least common multiple of 2x and 3x. And here we get 6x. So we would like one of these equations to have the term positive 6x, and we would like the other equation to have the term negative 6x. To make sure that those are opposites, we need to multiply the first equation by something to make it positive 6x, and multiply the second equation by something to make it a negative 6x. What we're going to multiply the first equation by is positive 3, because 2x times 3 is 6x. We're going to multiply the second equation by negative 2, because 3x times negative 2 is negative 6x. Now when you're multiplying the whole first equation by 3, whatever you multiply on the left, you have to multiply the same thing on the right to keep the equation equivalent. We have then, when we distribute the 3, we'll have 3 times 2x, which is 6x. 3 times 5y is 15y, equals 33. We're going to multiply the second equation by negative 2. And again, if we're multiplying the left side by negative 2, we need to also multiply the right side by negative 2. The resulting equation will be negative 6x minus 14y equals negative 30. The third step in using the elimination method is to add the new equations to eliminate a variable. We're going to add them straight down. Notice the first term here, we have a positive 6x and a negative 6x. These are opposites. Whoops. Okay, these are opposites. So when you add those, the positive and the negative one, that's going to equal 0. Now when we multiply or add the y terms together, we have a positive 15y minus a 14y, and that's going to leave us with just a single y. And on the right side, 33 is positive, and negative 30, when you add those together, you get positive 3. So y equals 3 is part of the solution to this system of equations. We're going to find the other value. If we know what y is, we need to work and substitute that into one of the original equations to determine x. You can use either the first or the second original equation. I'm going to use the first. The first original equation was 2x plus 5y equals 11. I'm going to replace the y in this original first equation with the y we found when adding the equations together. So we will get 2x plus 5 times 3 equals 11. We'll get 2x plus 15 equals 11, and then subtract 15 from both sides to get 2x equals negative 4, and then finally by dividing by 2 we get x equals negative 2. So our solution to the system of equations is the ordered pair where x is equal to negative 2 and y is equal to 3. Our last step in solving a system by elimination method is checking our solution. We want to check to make sure that negative 2, 3 is a solution to both equations. The first equation being 2x plus 5y, or 2 times negative 2 plus 5 times 3 equals 11. Again, always go back to the original equation. When you do that, you get negative 4 plus 15. That does equal 11, so it's true for the first equation. We also want to check the second equation, which is 3x plus 7y equals 15. So that's going to be 3x, or 3 times negative 2, plus 7y, 7 times 3. We want to make sure that is equal to 15. By simplifying, we get negative 6 plus 21, and that does equal 15. So we've done our last step is to check the solution. So our solution to the system of equations is the single point negative 2, 3. Now there are some special systems of equations. For example, 9x plus 12y equals 18 and 3x plus 4y equals 6. Now if you use the elimination method, you want to get either opposite x terms or opposite y terms. Now we'll see that if you multiply the second equation by 3, you will end up with exactly the first equation. These are the same equations. So when you graph the two lines are going to overlap each other. So there is an infinite number of solutions. And in fact, every single point that's on one of the lines is a point that's on the other line. So there are an infinite number of solutions. And the way we write our solution set is using this set notation, the squiggly brackets, xy. The solution is all the xy points such that the equation is true, 3x plus 4y equals 6. Now the graph of those equations, you'll see that the graph is actually two lines. You don't see the two different lines, but one line will appear right above the other line. So every single point that's on this line is a solution to the system of equations. We say the system is dependent and the lines are the same. All right, for this example, we want to use the elimination method to solve the system of equations. One way to do that is by getting opposite x terms. Now notice the first term is a positive 3x and the second term is 6x. So the least common multiple of 3x and 6x is 6x. So I would like one of these to be a positive 6x and one of these to be a negative 6x. Since the second one already is a positive 6x, we'll leave the second equation alone. But the first equation, we would like it to be a negative 6x. So we would have to multiply the first equation by negative 2. When you multiply the first equation by negative 2, multiply both sides of the original equation by negative 2 to get the equation negative 6x plus 4y equals negative 2. The second original equation already is the opposite coefficient for the x terms. And now when we add the two equations together using the elimination method, we have negative 6x plus 6x is 0. A positive 4y and negative 4y is also 0. So on the left side of the equation we have 0, and the right side of the equation we have 1. Notice that we end up with an equation that's 0 equals 1. Well, this is false. So we say it's never possible that 0 is equal to 1. So this system of equations has no solution. The lines have no points in common. So how is it possible that two equations that are both linear equations will have no solution? The reason that happens is that the two lines are parallel. The system is inconsistent. The lines have no points in common.